Now we come to an example. Imagine here a fire truck is driving this way at 50 meters per second, and then there's an observer here actually also driving towards the fire truck, right, 30 meters per second. So you're the observer, the fire truck is the source. The fire truck is sending out a siren, right, a blast at the frequency of 440 hertz, which is the A note in the musical scale, right? So then what will be the perceived frequency by the observer when that sound wave reaches them, right? Well, since the observer is moving towards the source, that will tend to increase the frequency, and the source is actually moving towards the observer also, so that will also tend to increase the frequency. So both effects are gonna combine to increase the frequency of the sound source quite a bit, right? That's what I did. Because the observer is moving towards the sound wave, that will tend to increase. So in the numerator you have to add. And because the source is also moving towards the observer, then you put a minus here, that will also tend to increase the frequency, right? Both effects. So then here we put 440. So what are we going to use for the velocity of the sound? Let's assume that the temperature in the air is 20 Celsius. So the velocity of the sound is roughly 343 meters per second. So we're just going to approximate. In a typical problem, what they might actually do is they might actually give you the temperature. So you would have to first calculate the velocity of the sound, 3. So convert this to Kelvin and put here 293 over 273 and square root it and then multiply by this. And you would get 343. So depending on what the temperature in the air is, you would have to first calculate it. So for this problem, let's just assume the velocity of the sound is 343. So we put here 343. Then we put the velocity of the observer, which is 30, divided by 343 minus, and then here we put 50, right? Wow, that is musical note. I can check it here on my phone. E is equal to 523.25 hertz, and then the note D, which is equal to 587.3 hertz. So it's not one of the musical notes exactly, but it is between the C and D. So you can see here the frequency increases quite a bit, right? Well, what's going to happen? Well, eventually the car is going to come here and then go this way, right? And therefore, if the fire truck is still driving this way and you are still driving this way, now both of you are moving away from each other, right? So the sound wave is going to be like very high pitch at first, you know, and then when you pass it, then the pitch is going to drop all of a sudden, and then it's going to be, oh, you know, then the pitch goes down. So then what's going to be the new frequency when you pass it and you're driving away, right? So then you're going to put here, this is going to be minus, and then this is going to be plus. You're both driving away from each other. 13 divided by 393 times 440. And now the frequency is equal to 350.4 hertz. That is very close to the musical note F. And the original sound note was 440, and it was an A note, right? When we were driving toward each other, the musical note went all the way to between C and D, kind of in between here. So when you're both driving away from each other, then the note turned into an F, which is the 350. And then this was 560, right? So it was between C and D. So you can kind of see here that the effect was pretty pronounced. Okay, now what could happen if neither of this is happening per second? So the fire truck is coming from behind you, but you are driving in the same direction as the fire truck. So is the frequency going to tend to increase? Well, this depends who's going faster, right? If the fire truck is going faster than you, then they will still be approaching you, so the waves are going to meet you faster than they should meet, right? So the frequency should still increase. So we have your F prime is equal to 440, 343. So because you are driving away from the fire truck, that tends to decrease the frequency, right? You're going to the right. So we put a minus here and we put 30, right? But because the fire truck is coming toward you, you put here 343 minus 50. The minus in the denominator will tend to increase the frequency. The minus in the numerator will tend to decrease the frequency. But because the fire truck's speed is faster, this number ends up being smaller than this number, right? So you have here 440, you have here 313, and then on the bottom you have 293. Well, because this is smaller than that, this ratio is greater than 1. Frequency still went up, but it didn't go up that much. So that one will be musical note 470. Well, it's between A and B, basically. 470, because the note B is 494. And if the opposite could happen, is if the fire truck was going 50 and maybe you were going 60 meters per second, or we could just switch their speeds. Let's say you were going 50 and the fire truck was going 30. We can see what that effect will be. On the numerator 50, and in the denominator we put 30. Just switch them, right? So then we have here on the top we're going to have 293, and then on the bottom we're going to have 313. Well, because the ratio is now less than 1, so then we can calculate what that is. That one is going to be 411 between G and A, right? So the G note is going to be 392 hertz. And then the A note we already said is 440, and so 411 is between the A and the G, 411.88. So it only goes up a half a step from A to like a half a step between A and B, and then down a half a step between A and G. But when you're both driving toward each other, it goes from A, B, C, 2.5 steps. 1, 2, 2.5 steps between C and D. Then it goes 1, 2, it goes 2 steps down. You can see here when to do the plus, when to do the minus, and the logic behind it, and what kind of answers you will get, and how to make sense of those answers. Okay? Thank you very much.